Greetings, math fans. All right, so this is day 3. We're going to talk about parametric differentiation. Okay, you guys remember we did parametric equations back in the day. So basically, what you do is you have an extra variable, right? You have another variable, and so you're going to have x and y in terms of another variable. We're going to call it t. So we're going to say this is a little wordy, but write this down here. The parametrized curve x of t and y of t is differentiable at t if x and y are differentiable at t. And y is a differentiable function of x. So let me just give you a quick example of an example of not differentiable. If I told you x equals pi and y equals cotangent of x. Okay, why is this not differentiable? Well, what's the cotangent of pi? It's undefined. So that's why this is not differentiable. Okay, so let's talk about a couple things here. First of all, we have our dy dt, derivative of y with respect to t, dx dt, derivative of x with respect to d, and our old standby dy dx, derivative of y with respect to x. And if I relate these by the chain rule, which you guys remember, we did that before with the u, okay, we can actually say dy dt, right? This guy, well, think about it. Doesn't that link them together? Okay. Ooh, look at that. Interesting. Dy dt equals dy dt. So actually, that's just one way to kind of link them by the chain rule. So if you remember, dy dx is equal to dy du. This is from back in the day, just to kind of have you recall. Dy du times du dx. Okay, and there's your link, right? There's your chain. So what I'm going to do is I'm actually going to, those three functions here, dy dt, dx dt, and dy dx, I can rewrite as dy dx. So dy is equal to dy dt over dx dt. Right? Don't you guys agree with that? Because I can multiply the top and bottom by dt. They cancel out, and I have dy dx equals dy dx. This, math fans, is like super important for parametric differentiation. Super important. Okay? So just kind of memorize that. You can kind of remember that is, again, dy dx, right? It's y over x, or the yax. That's the same thing with this guy here, too. Dy dt over dx dt. Okay? But that is really, 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 really important when we do parametric differentiation. All right, so let's start off with an example here. Find the equation of the tangent line to the curve at the given value of t. So it's kind of a generic direction. Okay, so here's your first example. X equals 2 sine of t, and y equals 2 cosine of t, and t is equal to 3 pi over 4. Okay, well, that's pretty easy. Again, we're just going to do dx dt. And again, don't make that don't do product rule here, math fans. You just say it's 2 times, and it's going to be, in this case, 2 cosine of t, and dy dt is equal to, derivative of cosine is negative sine, so it's negative 2 sine of t. So dy dx is equal to y over x, so it's negative 2 sine of t over 2 cosine of t. Okay, the 2's cancel. We wind up getting negative tangent of t. So this is the equation for the slope of the tangent. Okay, and then what we're going to do is we're going to plug in at t equals 3 pi over 4. I plug it in, and I get tangent of 3 pi over 4. Remember, anything pi over 4 is 1. And so in this case here, remember 3 pi over 4 is over here. And so it's negative, but we already have a negative here. So it's really equal to negative of tangent of 3 pi over 4, which is negative of negative 1, which is positive 1. That's the slope of the tangent at that point. Okay. Now I need to figure out an x and a y coordinate in order to come up with an equation. Well, you just plug in into the original problem, you plug in t is equal to 3 pi over 4. So x equals 2 sine of 3 pi over 4. So x equals 2, and sine of 3 pi over 4 is positive root 2 over 2. So it's equal to root 2. And y is equal to 2 cosine of 3 pi over 4. That's just 2 times, and this is negative root 2 over 2, which is negative root 2. Okay, so my coordinate is root 2 comma negative root 2. That's pretty easy. So now I have my slope, and I have my point. So my equation, the tangent, is y plus root 2 equals 1 times x minus root 2. Okay, and you don't even need this here, necessarily the 1, right? You can just leave it like that. It's cool. All right, and then just for the heck of it, the normal line is going to be y plus root 2 equals negative parentheses x minus root 2. Okay, so just be careful. If I ask you for the normal equation, that's what you're going to give me. If I ask you for the normal slope, you're going to say negative 1. Okay, that's pretty easy. Let's try one more example here. Same directions, x equals 3t squared plus 2t, and y equals 5t squared, and it's at t equals 2. Okay, so dx dt equals 6t plus 2, and dy dt equals 10t. Okay, so dy dx is equal to 10t over 6t plus 2, y over x. Okay, it's pretty mellow. And then let's say at t equals 2, so it's 10 times 2 over 6 times 2 plus 2, so you get 20 over 14, which is 10 sevenths. That's the slope of the tangent line. All right, and then I figure out my coordinate by plugging t is equal to 2, so x equals 3 times 2 squared plus 2 times 2. So x equals 4, it's 12, plus 4 is 16, and y equals 5 times 2 squared, so y equals 5 times 4, which is 20. So my coordinate is 16 comma 20. And so we have our tangent line. It's pretty easy. Tangent line is just going to be y minus 20 is equal to 10 sevenths times x minus 16. And then, of course, your normal line is just going to be y minus 20 equals negative 7 tenths times x minus 16. Okay? That's pretty easy. Pretty easy. So what I want to do, that's pretty much it with parametrics. I want to do one more composite function. So this is an extra composite function example. And we're going to have given f of x is equal to x to the fifth plus 1. G of x equals the square root of x. And at x equals 1 is what I'm looking for. So what I do was I want you to find f of g prime of x. And if you guys remember that, that's the same thing as saying f prime of g of x times g prime of x, right? That's the chain rule. So you do the outside first, and then we do the inside. All right? So let's plug things in. First of all, if I put a 1 in there, g of square root of 1, so it's going to be f prime of g of 1 is just 1, right? So if I put a 1 in here, that means I plug a 1 into there, square root of 1 is 1, and then times g prime of x. Okay, so I want to take the derivative, so f prime of x is equal to 5x to the fourth, and g prime of x equals, right, this is x to the 1/2, so it's 1/2 x to the negative 1/2. Okay, or 1 over 2 times the square root of x, any way you look at it. All right, so again, we're plugging in 1, so f prime of 1 is, because now we're doing, right, I'm solving for this guy right here. So f prime of 1 is 5 times 1 to the fourth power, which is 5. Okay, and if I put a 1 into here, g prime of 1 is 1 over 2 square root of 1, which is just 1/2. So it's really, again, it's this guy right here. Okay, and it's going to be f prime of 1, which is 5, times g prime of 1, which is 1/2. So my answer is 5/2. Okay, so that's a pretty quick lesson, but it's composite functions at the end there, and just using parametric differentiation for the other examples. All right, that's it, math fans. Have an outstanding day. Adios. Goodbye.